Hi, I'm David Dueber. I'm a student of Dr. Tolan's, and I'm going to be talking to you about mediation, moderation, and measurement error. Oh my. So the outline for this talk is first I'm going to give you a modern take on mediation analysis. Thinking about mediation analysis has changed a lot in the last, I'd say, 15 to 20 years. And so I'm going to give you a modern take on it, and then talk about a common problem in path modeling in general, but especially in mediation, called measurement error, and what we can do about it to get a better analysis. And finally, as time allows, talk about moderation as well, which is different from but often confused with mediation. So the first question is, what is mediation? Mediation is about explaining causality. So if some predictor X causes some outcome Y, we would like to know why. How does that work? Why, for example, does prior achievement in math say, if I did well in Algebra 1 in 8th grade, how does that explain how I do in geometry in 9th grade? My prior achievement will predict my final grade in geometry, but the question is why? Is it just because I've got math skills? But geometry and algebra as taught in our schools are very different from each other, so maybe that's not it. We might hypothesize and then do a study. We might hypothesize that there's a mediating variable such as self-efficacy. If I've done well in the past, I feel self-efficacious. I'm confident I can do math in school, and so maybe that predicts my success. So my prior achievement predicts my self-efficacy, which in turn predicts my performance in class. So that's mediation. Why does prior achievement predict future success? One reason, out of many, but one reason might be that it increases my self-efficacy. Mediation analysis comes from causal literature and especially from experimental studies. Most of the work in this area has been specific to experiments. And so I'm going to give you an experimental scenario also, just to have one in your mind. My children had a really hard time with daycare. I would drop them off at daycare and they would yell and scream and cling to me. And so the daycare, we did a little intervention. And what would happen was, when I came to drop them off, the teacher would come out to meet us. And so it worked really well. All of a sudden, my kids, they didn't mind very much when the teacher came to the lobby to meet us. And so a daycare, or a group of daycares, might say, okay, we've got this problem with kids behaving badly after they're dropped off. We're going to do an experiment. We're going to randomly assign some people drop off like normal. Randomly assign some other people, the same number, to when their kids get dropped off, the teacher comes and meets them in the lobby. And then we're going to monitor behavior at the end and see, does the group with the intervention behave better than the group without. So classic experimental study. We're doing an intervention, seeing how it affects, in this case, behavior of small children. And if it works, I might ask myself, why? Why does that help? And a possible mediating variable, a possible reason that intervention could help, is if it increases secure attachment. So secure attachment is how strongly you feel connected to and supported by, and all those things, a person. So if their secure attachment with the teacher is enhanced because the teacher comes to them, that might explain why their subsequent behavior is better. So it's about explaining why your intervention worked. Okay, that's mediation in a nutshell. So the big question is, how can I tell if mediation occurs? And thinking about this exact question has changed radically since Barron and Kenny introduced rigorous mediation ideas in 1986. And the current thinking is pretty simple. In this path here, where X predicts M, X and M both predict Y, there's a direct effect from X to Y, B1. And there's additionally an indirect effect, X through M to Y. And the strength of that indirect path is B2 times B3. If that product, the indirect effect B2 times B3, is significantly different from 0, then we say, okay, we have an indirect effect. We have mediation. X is in fact a mediator. Something real is going on. And once you have that product, B2 times B3, anytime you fit a model using a computer program, you get an estimate. It's not really what happens. It's an estimate. There's all manner of sampling error, for example, that can cause it to be different from the population value. And the distribution for this indirect effect B2 times B3 is very complex. It's not nice normal distribution, and we can do t-tests. The current thinking is that the best way to assess this indirect effect, whether or not it's different from 0, is to use bootstrapping and create a parametric confidence interval using bootstrapping techniques. Now, for some of you, bootstrapping might be a really new idea. I say bootstrapping, and you think, oh, what does that have to do? Pulling yourself up with your bootstraps. Well, that idea, pulling yourself up with your bootstraps, is actually what bootstrapping is about. Our little technical definition here is about creating a sampling distribution. Right? Anytime I have a population and I sample from it, that sampling technique has a distribution to it. So my parameter of interest, it has a distribution based on that sampling. So if I were to sample from the full population, a lot of times, the distribution of my estimate for my indirect effect would mirror some population sampling distribution. And the problem with indirect effects is that we don't know what it is, so we're going to have to make it up. So what we're going to do is we're going to collect some data. We have a sample. And that'll generate one estimate. But I want a whole distribution of estimates. So what do? I pretend that my sample is my population. And I resample from it with replacement. So if I've got 500 people in my sample, I'm going to take those 500 people, and I'm going to sample 500 people from them, but with replacement. So maybe person number 7 gets sampled 12 times. Maybe person number 36 doesn't get sampled at all. I sample from that with replacement. I pretend like it's my population, and I'm going to keep sampling it from it, each time creating a parameter estimate. After 1,000 times of doing this, I've created 1,000 samples and come up with 1,000 estimates. Those 1,000 estimates will have create a distribution. And it's my hypothesis, when I bootstrap, that that distribution of parameter estimates is in fact the sampling distribution of the population. It's actually the sampling distribution of my sample, but we hope when we do bootstrap, and we should never use bootstrapping with very small samples like 30 or 50 people, it wouldn't work well. But with large samples, it's reasonable to expect the sampling distribution of my sample to be the same or very similar to the sampling distribution of the population. And so once I have that distribution of parameter estimates from my 1,000 times of resampling data, I can use a confidence interval. So what's the 2.5th percentile parameter estimate? What's the 97.5th percentile parameter estimate? If those are both positive, then I can be confident with an alpha level of 0.05 that my indirect effect is also positive. Okay, so one major advance, I think, that's happened in the causal literature is insistence on time precedence. To establish that causality is happening, that X in fact causes M and M in fact causes Y, if they're all happening exactly at the same time, I can't tell which one causes which. Maybe M causes X. Well, not in an experimental setting, but if X is, even in an experimental setting, if X is my experimental treatment effect, treatment versus no treatment, well, how do I know which place M and Y should go? So even in experimental settings, there needs to be careful consideration of the directionality of causality between variables and whether or not they're not simply caused by some third variable that we're not even measuring. So Cole and Maxwell in 2003, they and another co-author have an updated paper in 2011 that's a bit of a harder read. So I listed this reference here because it's a pretty basic introduction to thinking about time precedence in causality research, and especially in mediation research. They said, okay, if we want to be sure that X is causing M, what we could do is that initially, when we set up our study, we can measure both X, our predictor, and M, our mediator, and use both of those to predict the mediator at a later time. 6 months later, we're going to administer our survey or whatever it is that we're doing, and we're going to collect data on M. So, because maybe my variability on M is just because of pre-existing variability on M. Maybe it's not because of X at all. And so if I account for variability in M from a previous time point, from time 1, then I can be more confident that changes in M from time 1 to time 2 are the result of, in fact, my X variable. And similarly, we can do the same thing for y at a third time point. So with observational data, there's 3 different time point method for designing a mediation study is pretty standard. There are 2 time point versions as well, called partially longitudinal. Anyway, we want to make sure that x causes m and that m causes y. And that is not as simple as, well, it looks that way to me. So you can't just put arrows in your model for no reason. You need a really strong reason. Temporal precedence is a good way to do that.
Question.
Yes?
Why partial? You
Oh,
have 3 times.
Yeah. So I said there are models that do this with only 2 time points, and they're called partial longitudinal mediation analysis models.
2 times.
Yeah, you can Google that if you want. So, little audience participation time. We got 2 variables, motivation to learn college algebra and self-efficacy in college algebra. And they both cause success in college algebra. We can measure them at the beginning, and we can see how you did at the end of the class. So your motivation, your self-efficacy at the beginning, they happen before you experience that success, time precedence. But the question is, would it be mediation or would it be hierarchical regression? So when we're looking at these 2 models, they look very similar. The only difference between the top model and the bottom model, they're arranged differently. But the only real difference is that in the bottom model, motivation to learn college algebra causes self-efficacy, whereas in the top model, they're correlated, but we make no hypothesis about that correlation. Okay. So do anyone have any ideas which of these models makes sense to you? Does motivation cause self-efficacy, which causes success in college algebra, or are they just related variables that both have a causal effect? Who's got a thought?
Number 1.
Ilya says number 1, and he's right. Your motivation and your self-efficacy don't, in literature, people haven't found a causal effect from motivation to self-efficacy, at least in the context of this one single college algebra course that we're taking as college freshmen. So this example I gave might be more appropriate to use a hierarchical regression model for. When you have several different predictors of an outcome, it's sometimes very difficult to know what exactly the relationship is between them. And so your prior literature, the design of your study will help you figure out what model to be using. All right, so I have an empirical example for you. This example and the moderation empirical example both use real data from a different context. So, all of these effects are effects that were actually found in real data, but they did not apply to these variables. I had to change it. Okay, so our question is, academic achievement causes happiness. Okay? And the question is why? Why would doing better in school make me happier? And our hypothesis is, well, doing better in school makes you happier because doing better in school increases your self-esteem, which in turn increases your happiness. I want to reiterate this as many times as I can. Mediation is about explaining causality. Why does academic achievement influence happiness? That's a mediation question. Why? Okay. So I've collected data on these 3 variables, achievement, self-esteem, and happiness. Perhaps I have an achievement GPA or something. Maybe I have a self-esteem self-report scale, and I have a happiness self-report scale, and I'm going to give them to you, and we're going to add up all your items, and then we're going to analyze these variables. Okay. In M+, if you're not familiar with M+, that's okay. The important part is the model command. On is the command for regression. So self-esteem on achievement means that self-esteem is regressed on achievement. Achievement predicts self-esteem. And similarly for the second line, happiness is predicted by both self-esteem and achievement. So this model that I've drawn down here is reflected in that model statement. And if you're doing mediation analysis in M+, they have a happy sub-feature to the model command called model indirect, where I can put my outcome, happiness, and then IND for indirect effect, and then my predictor achievement. And in more complicated models, where I might have several mediators, maybe there's 50 different paths going on, it's a crazy complicated model, this will find and analyze all indirect effects between happiness and achievement.
Based on the user's guide, I put in a mediator in the indirect command.
Mhm.
Does it matter then to?
So you can put happiness, indirect, self-esteem, achievement.
Mm-hmm.
And so what that does is if you put any variables before your final predictor of interest, it will only find the indirects that go through that mediator. So if I had self-esteem, I had another variable down here, this command would look at both of those indirect effects, but happiness, indirect, self-esteem, achievement would only look at that indirect effect. And so there's a lot of fine-tuning available in those commands. Except in very complex models, since it breaks down every single different indirect effect for you, I'll just ask for all of it. Do outcome indirect predictor. You may, if you have a more complex model and a specific research question, you'll want to build that indirect statement to suit your research question, of course. And we're bootstrapping. So when you don't request analysis bootstrap, what M+ does is it creates standard errors, it estimates standard errors, for all the different parameters, and then uses z-tests to determine whether or not those parameters are significant. So, but if you use bootstrap, it creates that sampling distribution. And down here I have C interval for confidence intervals, bootstrap. So it's going to take that bootstrapping sampling distribution and use that to create confidence intervals for my effects. So the output, there's a lot of output. If you've used M+ before, you know you get pages and pages and pages of output. But I'm going to stick to the confidence intervals for the standardized total, indirect, specific, indirect effects. I'm using standardized so that I can compare this model to one that I'm going to run shortly, in which the unstandardized effects would not be directly comparable. But if your predictor, for example, is a treatment condition, 0 versus 1, you wouldn't want to standardize that. Okay, so just because I'm looking at standardized effects here, I'm not trying to say when you're doing mediation analysis, just look at standardized effects. No. Look at the effects that make sense. If your scale of your variables are interpretable, then don't create standardized effects. If you have a treatment effect causing something measured in dollars, well, I can say, hey, doing this treatment will save me $1,000. That's very directly interpretable. I don't need to standardize it to create an interpretation. Standardizing it is nonsense because my predictor is binary. So I'm standardizing because it's going to be relevant for my next example, not because I recommend you always do that. Anyway, it gives us estimates for a total effect, a total indirect effect, an indirect effect, and a direct effect. The direct effect was the path on the bottom that didn't go through self-esteem. And then it'll list all of my specific indirect effects between happiness and achievement. If I had more variables in there, it would give me a lot of different lines here. And so what we see here is that the specific indirect effect has a standardized effect of 0.156, and I can use my confidence intervals to essentially do a significance test. The lower to upper 2.5%, that's my 95% confidence interval, from 0.071 to 0.241. Since the 95% confidence interval is entirely negative, it does not contain 0, then I can conclude that my indirect effect is significantly different from 0. So that's my test of significance right there, whether these two numbers are both positive.
I don't know if you're going to get into this later, but what would you suggest about bootstrapping if you have skewed data so we can't use like MLR and bootstrapping at the same time?
Right. So MLR accounts for things like non-normality by using two different ways of estimating the standard errors and balancing them. But it assumes, at the end of the day, it assumes that the sampling distribution is symmetric. And so if you ask yourself, okay, my sample is symmetric, but what about in the population? If you think that in the population you have a symmetric distribution, a normal distribution, you might make different analytical choices than if you think that the distribution in your sample is reflective of the truth. Okay? So that's my kind of cop-out of saying it's complicated. I would have to know the specifics of your case, and I'd be happy to talk to you afterwards. But generally speaking, in large enough samples, bootstrapping should be reliable. And especially when the effective interest does not have a symmetric sampling distribution. Okay, when your parameter of interest has a symmetric sampling distribution, you're usually okay using MLR. Anyway, back to here. We have a significant indirect effect. Yay! Okay, so we can write this up in our APA style, so we can get our publications. And we'll talk about, hey, here's my standardized indirect effects. I'll list the 95% bootstrap confidence interval and an effect size. Kappa squared is an effect size for mediation, and it doesn't have a very clear interpretation. Preacher might disagree with me, but I don't think it has a very clear interpretation. But like every effect size, it can be compared across studies. Okay? Even that standardized indirect effect is hard to compare from my study to your study. We both study the same thing. Look, I have a higher standardized indirect effect. Does that mean I had more mediation? Maybe not. But kappa squared, we can compare across different studies of the same phenomenon. So that's all well and good, but there's a big, big problem with everything that I've said so far, and that is, what if your variables have low reliability? I said, what if we had this measure of self-esteem, and it was these 10 items, and they're in Likert type, strongly disagree up to agree, and we coded them 0, 1, 2, 3, 4, and then we added them all up. Well, what if that measure had low reliability? What if alpha was 0.7? Well, it turns out that when the variables in your mediation analysis have measurement error, there can be substantial parameter bias. Let me go back to a picture. Specifically, I'm not going to go into this too deep because it gets complicated, but if there's measurement error in self-esteem, that will diminish the size of both paths involving self-esteem, and it'll, because those paths are smaller, to account for the correlation between academic achievement and happiness, the direct effect gets much bigger. And measurement error on each of the other variables has their own effects. But generally speaking, when we have measurement error in all of our variables, we expect to get smaller parameters than if we didn't have measurement error. So we're underestimating what's really happening. And especially when we have measurement error in our mediator, we can underestimate our indirect effect compared to our direct effect. And we'll see that in this example in just a minute. So if we have a lot of measurement error, what should we do? Well, from a design perspective, we should get better instruments, right? If you have an instrument with a measurement error with a reliability of 0.6, probably shouldn't be using that instrument. So the best thing to do is to minimize measurement error. If you're designing your instrument and you really want that very high reliability, maybe add more questions to it. Maybe throw out a couple questions that don't represent the construct very well. Minimize measurement error. Even if you're going to do techniques 2 and 3, regardless, if you're doing research, minimize your measurement error as best you can. You can't minimize all measurement error. That's life. It doesn't happen. So what should we do? Well, one suggestion is to account for measurement error using structural equation modeling techniques. Instead of measuring self-esteem one way, I can measure self-esteem with 3 different instruments, or maybe from 3 different sources. I can ask you to self-report your self-esteem. I can ask your teacher about your self-esteem. I can ask your parents about your self-esteem. I can ask a friend of yours about your self-esteem. And I can combine those informations to get a better picture of your true, it would end up being latent. We can't observe it directly, but your true self-esteem might be measured more accurately using multiple measures. And if you really honestly only have one source of measurement for your variable, it can be corrected for measurement error. This practice was first proposed by Hayduck in 1987. But this DeShawn 1998 paper, every reference in here, I have a slide at the end that includes all of them. The slides will go up on the APS Lab website after the talk, so you can look at them later and say, oh, correct for measurement error. I need to go know about that. So you can look it up. You don't have to remember DeShawn 1998. There's a technique for correcting for measurement error when you only have a single indicator for a construct. And it's, I will give you a warning, it is a little bit contentious. So, what if I had designed this study a little differently? And my academic achievement had 3 different measures of academic achievement. You know, a GPA, your ACT score, and how many scholarships you got. 3 different ways of assessing academic achievement. And 3 different ways of assessing happiness. But I still only have that one way of assessing self-esteem. So I'm using that trick, that number 3 on the previous slide, of correcting for measurement error, creating a single indicator latent variable, and fixing the residual variance of the self-esteem measure to its unreliable variance. So if it had a, reliability of 0.7 and a variance of somewhere around 240, then the unreliable part 0.3 times 240, bam, that's where I got it.
Reliability is a measure of consistency of responses. It's not actually indicating what you measure is what you measure.
Right.
You think you're measuring.
Yes.
Is what you're measuring.
And so that's a very good point, that if I have 3 different ways of assessing happiness, and I use all 3 of them, I get better construct representation. I get more, this is a construct validity, a really good thing for construct validity, right? I'm not relying on researcher A's way that he thinks that happiness works, researcher B in the way she thinks about it, and research team C in the way they think about it. All those different instruments can be used to get a better representation of the construct. So from a measurement error standpoint, but also from a validity standpoint, from a construct validity standpoint, this is better. Yeah, and we don't get that bump in construct validity when we use this single indicator latent variable approach. But we can somewhat account for measurement error. Okay, so I have the same question. Does self-esteem mediate the influence of academic achievement on happiness? And I'm going to essentially answer it in the same way. I'm going to compute path coefficients for these paths and multiply these 2 to get the indirect effect and see if it's different from 0. The only difference now is I have latent traits measuring academic achievement, self-esteem, and happiness. Using my instruments, maybe with some scores, or maybe GPA is just a number, as indicators on those latent variables. Okay. So the M+ syntax looks quite a bit more complicated. There's a measurement part of the model in which each latent variable is measured by its indicators. So achievement, ACH, is measured by the 3 achievement measures. Happiness is measured by the 3 happiness measures. And self-esteem is measured by its 1 self-esteem variable. And then this line here fixes the residual variance of self-esteem to what I've calculated outside of this. I've calculated what the unreliable variance of self-esteem is. But these 2 lines here, the structural part of the model, look exactly the same, right? Achievement is predicting both self-esteem and happiness, and self-esteem is predicting happiness. And that's the exact same model indirect statement, and requesting the exact same things in output. So nothing's really changed except how I'm measuring each of my traits. They're now latent, measured by several things. The output looks shockingly similar, except the numbers are different, and I'll get to that momentarily. I have different estimates for each thing, but I check to see if they're significant in the same way. I look at the 95% confidence interval from the lower 2.5% to the upper 2.5%. The indirect effect is statistically different from 0. The direct effect is not. The 0 is contained inside its 95% confidence interval. So this coefficient is not significantly different from 0, and we'll talk about that momentarily.
In the previous model, before you went to structural equation model, you had the direct effect larger compared to the indirect effect.
We'll get to that.
Okay.
Just hold your horses.
Okay, I'm holding.
Okay. So I say that with my kids, and they grab something and pretend they're riding horses. So
Yeah, 3.
So we're going to compare these models. Now, okay, I know what y'all are thinking. I added new variables in the structural equation model, and I shouldn't compare coefficients directly. You're absolutely right, I shouldn't. So what I did was I took the observed model and corrected all 3 variables for measurement error to get this bottom row. Okay? And what the big thing to notice is that the indirect effect is much larger in these models that corrected for or accounted for or corrected for measurement error. We say that structural equation modeling accounts for measurement error in the way that the latent variables are constructed, and this single indicator latent variable approach I was telling you about, it corrects for that measurement error. Anyway, the indirect effects were about 1.5 times as large. That's a really great improvement. Okay, if I'm publishing and I have my effect sizes, if I have a much bigger indirect effect, I've done a better job of explaining. So these 2 models below, inside the model, more of the effect of achievement on happiness was explained by self-esteem in the models that accounted for or corrected for measurement error. So that's really great. That's fantastic. But if that's not hugely motivating to you, because you know what, they're all statistically significant, I get my publication anyway. What about the total effect? Remember how I said that in the model accounting for measurement error, the structural equation model, the total effect was not significantly different from 0. Well, I can run another model where I leave this path out. If you leave a path out, that's the same as fixing it to 0. This path is 0. Yeah. So we can run this separate model. Here was our original model from before. They gave you some fit indices, excuse me. And our model with no direct effect, I left out, all the indicators because it's just noisy. And it has these fit indices. And if fit indices aren't your thing, don't worry about it. The point is that, over here, smaller is better for SRMR, bigger is better for CFI, TLI. So they don't look very different from that standpoint, but we can compare models with a change in chi-squared. It's really a change in log likelihood test, a delta chi-squared test. So we changed one path. We took one path away. So our test in the change in model fit has one parameter, and the chi-square size is just the difference in chi-square statistics. And so I can, get out my Excel and ask it for what the associated p-value is with that test. It says it's 0.188, and that the RMSA, CFI, and TLI, I could have said and Sturmer, are all pretty similar. And so, what does that mean? Well, this is a test to see if this fit is significantly better in the more complex model, and no, it's not significantly better. So the simpler model, with this path removed, fits as well as the model with that path intact. And so that's a totally substantial, from a substantive standpoint, that's a different model. We're having a different explanation of what's going on. In the model with the direct effect in, we're saying some of the effect of achievement on happiness is caused by increase in self-esteem. And here we're saying that self-esteem fully mediates or fully explains influence of academic achievement on happiness. And we can list all those standardized effects and so on and so forth. And that's a much stronger statement than we had before. This is a really powerful, really cool statement. I do want to warn you against overgeneralizing or over-interpreting when you have this full mediation. And that's because of possible confounding effects. I forget what the word is. If we had included other predictors, they might have changed that situation. So if we had another possible mediator, maybe we have 2 different mediation effects, they both kind of cancel out, and then the total effect comes back in. So when you include more variables in your model, suppression, thank you. There could be suppressor variables that we're not including in our model. And if we were to put them in our model, the paths would look different. So don't say, because of this, that the only reason you're happier because of achievement is that your self-esteem improves. That's not a statement we can ever say, statistically. It's physically not possible. There are an infinitude of variables that can affect your happiness. So don't make a statement like that. But from a modeling context, we've shown that the simpler model, without that direct effect there, it works perfectly fine after we've accounted for measurement error. Okay? And that's still a really cool thing. All right, so that's the end of mediation. So if anyone has any questions about any of this stuff, I'd be happy to take a stab at answering it. Yeah.
Where did you get the kappa squared from your previous?
Oh, kappa squared, I've got this citation on the slide. It's from Preacher and Kelly, 2011.
Okay, so that wasn't something you found in your output, you calculated that.
Right.
Oh.
You'll find that a lot if you're used to using SPSS, that it calculates every effect size under the sun for you. And if you want effect sizes in M+, you break out Excel and you compute it yourself.
Unless somebody's created an online calculator.
Unless someone has created an online calculator or a macro. And in fact, I used I used an online calculator for this kappa squared, because kappa squared is a bit of a pain to compute.
If you have multi-level data, like longitudinal or dyadic data, does anything change significantly, or?
Yes. So, do I have a good picture for this? I guess the best picture to talk about that is here, and I do wish that the X had been on top, because sometimes, especially here in education, we'll have a predictor at a teacher level and an outcome at a student level, so they'll be at different levels, and that doesn't change the design very much. It does change the analysis quite a bit, and I'm not going to get into that because we're keeping things as conceptually basic as we can, but I do have a reference at the end that specifically speaks to how to do this in the multi-level setting. And if you're really, really interested, send me an email, because while I was at a conference last weekend, I found another really good reference. Oh, wait. Okay. So, moderation. Mediation and moderation often go hand in hand, and because they're both about, there's this relationship, X predicts Y, and it's about analyzing that relationship a little bit deeper, and their names are similar, and people confuse them for each other. And I think those are the three big reasons that they always go hand in hand. But they're very different things. Okay? So moderation, Z moderates the effect of X on Y, if that effect is different for different levels of Z. So an experimental, again, a lot of moderation analysis came from experimental settings. An experimental place that this might happen is if I make Brussels sprouts, and I'm the only person in my family who likes Brussels sprouts. But I could do an experiment. I could make Brussels sprouts with bacon on them. And I know that a couple people in my family are going to eat them because of the bacon. So I might say, hey, maybe I could get lots of people to like Brussels sprouts because I could put bacon with them, and then everyone will like Brussels sprouts. So I have this hypothesis that including bacon on Brussels sprouts increases enjoyment of Brussels sprouts. So I've got treatment effect, bacon or no bacon, and how much people enjoy Brussels sprouts as a result. Like, hey, there's this positive, there's going to be this positive effect there. But then I think about some of the people in my extended family, and they don't eat meat. They don't eat bacon. So if I put bacon on their Brussels sprouts, they're going to get really upset at me. They're going to be like, you just ruined the Brussels sprouts. There's all this bacon fat in my Brussels sprouts. I can pick off the bacon, but it was still cooked in animal fat. I don't want to eat that. So being a vegetarian moderates the effect of bacon in your Brussels sprouts on your enjoyment. I could hypothesize, just study, but I could hypothesize that the effect of bacon on enjoyment is positive for populations that like meat and negative for populations that don't. So it's different depending on which group you belong to in the moderator, whether you're a vegetarian or not. So that's an example of moderation from an experimental standpoint. And in this case, both of these variables were binary. And so I know a lot of cases in education, we will have treatment condition variables, but a lot of times we like our continuous variables. So a continuous example could be if my I'm going to miss the word. If my depressive symptoms can predict my academic performance. People who get depressed, they don't perform as well, right? But that relationship, depression or depressive symptom predicting performance, academic performance, it works differently based on your level of social support. People who have a lot of friends in their classes, if they're depressed, they might still be going to those classes because they have friends who drag them there. Or you're going to come study with us, right? But if you have low levels of social support, you might just stay in your room. And you might not achieve as much because you haven't been exposed to the material as well. So we might hypothesize that the effect of depression on academic performance is moderated by social support. Your depression doesn't cause your social support. It might, over time, you will get less because you isolate yourself from people. But in the instant where you get, I'm depressed now, that doesn't change your level of social support. So social support and depression are more or less unrelated to each other, in much the same way of random assignment of bacon is totally unrelated to whether or not you're a vegetarian. They're unrelated to each other, but this moderator variable z affects the level, it affects the directionality or the strength. It doesn't have to affect the directionality, it could just affect the strength of x predicting z. Okay. So, how can we tell if moderation occurs? This picture over here, this conceptual model, in which z influences the effect of x on y, it's a neat conceptual model, but not statistically. There's no statistical analysis for that. And usually we assess moderation based on the influence of an interaction variable, x times z. We're going to take levels of our predictor, levels of our moderator, multiply them to create a new variable. So for every person in our data set, what's your x value, what's your z value, x times z, that's xz. Okay? So everyone gets a score on that. We multiply the x and z variables together. And if this interaction variable, x times z, significantly predicts the outcome, then we can claim that moderation occurs. Now, I should have said on this slide, but I didn't, that we assess that not from is this coefficient different from 0, but rather from a hierarchical regression standpoint. If I add the xz term into a model, so I start with xz, I add an xz term, do I get a significant change in r squared? Okay. That would be how this is assessed. So,
significant or meaningful?
Well,
Because it can be
do you
significant,
have-
but the meaning
yeah.
is like 2 seconds on 2 minutes.
So the answer is yes, right? Are you interested in whether there's a statistically significant moderation or a meaningful moderation?
Yeah.
So that said, moderation is a bit of a tricky thing. Delta r squared is kind of sort of an effect size for moderation, but I'm not sure I would look at it and say, oh, it's only 0.04, this doesn't matter. We'll see later some graphs you can generate to really get a grip in your own head about whether or not it's important. But it's an important question, yeah. Same thing with indirect effects, with mediation, right? If the mediation effect is 0.003 and the direct effect is 0.8, well, newsflash, you didn't explain very much. Yeah. So, to really get a grip on what's going on, we have to look at some equations, right? Everything we're talking about is regression. So x, z, and xz are all predicting y, which means if we were to write an equation for y, there would be an intercept plus x's influence, b1 times x, plus z's influence, b2 times z, plus xz's influence, b3 times xz. Of course, we can never predict anything perfectly, so there's some error on the end. So if we're interested in how the effect of x on y changes for different values of z, I'm going to factor x out of those two terms. And so the coefficient of x is b1 plus b3 times z. So I can think about this, if B3 is big, then, for large values of Z, that coefficient is going to be bigger than it is for small values of C. So think of this as the slope of y on x. So the coefficient of x predicting y. And it's different for different values of z. That's really what I'm trying to say in this second line. All right. So do we have to worry about that whole time precedence business? Yes, we do. I didn't cite it on this slide, but somewhere else in the slide I cited Kramer and other people in 2008. They have a great explanation of the modern way of thinking about mediation and moderation. And there's two kind of criteria for claiming moderation exists. One is that the moderator and the predictor should be independent. Remember my two examples? Vegetarianism and random assignment, they're not related to each other. Depressive symptoms and social support, they might be related to each other, but not hugely strongly. People with friends, they get depressed too. And the second criteria is that the moderator must temporally precede the predictor. So the moderator is something that comes first. I was a vegetarian or not before this little experiment assigned me to bacon or not bacon. So the moderator comes first before the predictor, and then the outcome comes last. So whereas in mediation effects, temporal precedence was first comes the predictor, then comes the mediator, then comes the outcome. In moderation, the moderator comes before the predictor, which in turn comes before the outcome.
So you have
And
to
as Marky Mark reminds us, causal language in the absence of longitudinal data will get you dinged by some reviewers.
So you have to be first vegetarian in order to get into the experiment, right?
No, more, say, in this room, I could do this experiment right now.
Mhm.
I could give 4 of you Brussels sprouts with bacon and 4 of you without. Whether or not you're a vegetarian, and I don't know if any of you are or not, whether or not you're a vegetarian, it happened before you got into this room. So, sort of
That's
your
okay.
your personal properties are, they would always precede an experimental condition.
That's right.
And so a lot of times, so that's one way that we can talk about temporal precedence without having to do a longitudinal study. I don't have to ask you now whether you're a vegetarian, so that 6 months from now I can assign you degrees. That happened before. Likewise, your past performance, if I ask you what your GPA was as an undergrad, that's in the past. I don't have to wait 6 months before I ask you what your GPA is now. Or things like your gender and your ethnicity. Those things they happened before the study happened. Even though I'm not asking about them until the study happens. Anyway. All right. So, mediation and moderation, they get confused with each other. They're both about, more deeply analyzing this effect. In our case, of depressive symptoms on academic performance. And so, because they're both looking at that same thing, it's easy to confuse them sometimes. So, I just gave this example. I should not have given you that one verbally. So, we all know that social support moderates this relationship. But when you're, especially your first, for me, the first 50 times, you're trying to construct a model, really, really step back and think about it, and say, okay, I've got these 3 variables. How do they work together? Does it make sense that my depressive symptoms that I'm having now would influence the social support my friends are giving me? Well, no, because they were my friends before I got depressed. Now, if someone's been depressed for a very long time, that changes things. But if we're talking about people with new depression diagnoses, for example, your social support is largely independent of that because the things in your social life, they happened before this depression thing happened. So this doesn't make sense. I couldn't use depressive symptoms to predict social support in the context that I'm given. I could certainly design a different study in which, over time, your social support might change related to your depressive symptoms, but that wasn't the context I was giving. So in the context I was giving, this model makes more sense. So, another big red X. So it's time to look at how we would analyze moderation. And just a warning, it gets a little bit more complicated. Here's our research question. Does socioeconomic status moderate the influence of college navigation self-efficacy on college navigation goal setting? Now, college navigation self-efficacy, college navigation goal setting. So college navigation is something that we like to measure in high school juniors and seniors. It's about applying to colleges, applying for scholarships. It's about submitting this form for the FAFSA and all those sorts of things. So your goal setting would be things like, I have a specific date by which I'm going to submit my application to UK, or I know when the FAFSA is due. And college navigation self-efficacy are things like, I am capable of filling out the FAFSA. I think I'll be able to do a good job submitting my application to UK. So does socioeconomic status moderate that? So if you have high self-efficacy, your goal setting, I think I can do these things. Does your goal setting, I'm going to do it by this day, does it change based on your by your socioeconomic status? Okay. So again, to assess whether or not moderation exists, and we would have to have to separate the effect of self-efficacy on goal setting, we'd have to be careful about that. Socioeconomic status happens before, right? I don't expect that a 17-year-old might have changing socioeconomic status, but for the most part, it's determined by their path trajectory of their life. But as far as college navigation self-efficacy and college navigation goal setting are concerned, I have to be very careful in my experimental design and my justifications for why I can claim that the arrow goes this way. But I'm pretty happy about SES causing these things. Okay. So I have one model, a regression model, without the interaction effect, without the interaction term, and one with the interaction term. And the test for whether or not moderation happens is whether or not the second model explains a statistically significant amount of extra variation. So delta R squared. In the supplemental files for this talk, which will go up on the APS Lab website probably this afternoon, you can find the results of these two models. And there's a change in R squared. There's an associated F test that I can put on there as well. And it has a p-value of 0.001. So the p-value is less than 0.05. I can reject my null hypothesis that these models explain the same amount of variability. Therefore, I'm okay saying, hey, I have a moderation effect. Now that I've established that there's a moderation effect, let's look at it. And here's the n plus input. And I said it got a little bit more complicated. I didn't lie. So the first things first, when we're assessing moderation, when we're creating interaction terms, and a lot of times when you're doing regression in general with variables that don't have a specific meaning to 0, it's common to mean center, to subtract the mean, the grand mean from all the values of the variable, to center the variables at 0, so that an intercept, for example, would mean the value of college navigation goal setting when all the other variables are 0. Which, after we've mean centered, would mean at their mean value. So the mean value of college navigation self-efficacy and socioeconomic status. Anyway, so we mean center first. It's important to do before you create an interaction term, reasons for which are beyond the scope of this talk. And what we're going to do, right, is we're going to say, look, if we have moderation, we think that this effect is stronger. I forget which one is stronger and which is lower. It's different at low values of SES than it is at high values of SES. So normally the way to assess that is to pick 3 different levels of your moderator. If your moderator is binary, it's just yes or no. If your moderator was gender, for example, we could do it with a male group and a female group. But here we have a continuous moderator, and we're going to pick 3 different levels in the moderator. The standard is to do -1 standard deviation, 0, the mean, because remember we've mean centered, so 0 is the mean, and +1 standard deviation. if you have a particular variable for which there is an interpretable interval that would be useful to you, I really want to know what a difference of 10 looks like, well then do that. If there's no interpretable scale to your variable, and SES is maybe some survey where we add some stuff up, this particular variable is on a scale of 0 to 100. It doesn't really mean much. So negative 1 standard deviation, 0, the mean, and plus 1 standard deviation. And I've created these 3 variables under my model constraint, which allows you to declare new variables, and I can label my parameters. So CNGS on CNSE, B1. That means that B1 is the value of the path coefficient of college navigation self-efficacy, predicting college navigation goal setting. So I can use those labeled values, new values I create in my model constraint setting command to calculate stuff. So this is the simple effect of college navigation self-efficacy on college navigation goal setting at low values of SES. All right? If you remember from that slide where I factored out the x and it looked like B1 plus B3z, that's what this is. This is the slope of CNGS with respect to CNSE at low self-efficacy. So I'm going to pick a particular value, minus 1 standard deviation, plug it in there. This is my slope at a low value when SES is 0 and when SES is high, plus 1 standard deviation. Okay? So those are the 3 slopes. And what I can do in M+ is I can create a plot where this looks really complicated, and it is. I'm not going to lie. But college navigation self-efficacy at low values of SES, what it is if I have low SES, negative 17.023, whatever that is, I can look at the resulting regression equation using college navigation self-efficacy to predict college navigation goal setting and graph it. That's it. So I'm fixing self-efficacy. Now the only 2 things that are changing are college navigation self-efficacy and college navigation goal setting, and I'm graphing that regression line. Okay? And I can do that for my 3 different values of SES. I'm going to get 3 different lines. And so when we talk about what the effect of moderation is, sometimes we'll say, look, these 3 slopes, they're very different from each other. So a lot of moderation happens. Sometimes we'll look at these graphs, and I only graphed 2 of them. Because it gave me the confidence intervals, and if I put all 3 of them on, it was really noisy. But I could say that low SES, this is the regression line using CNSE to predict CNGS. And at high SES, this is the regression line. The bold red one for low SES, the bold blue one for high SES, and the non-bolds are the confidence intervals. Mm-hmm. And so there are all manners of tests I can do to determine the regions of significance. When is college navigation goal setting significantly different at low SES versus high SES, and so on and so forth. But what I got here is I've got 2 different regression lines using college navigation self-efficacy to predict college navigation goal setting. And they look pretty different to me. You'll have to, when you're doing your actual study, you'll know what the scales mean. They'll mean something to you. These are just some numbers, right? But in your own study, you'll be able to say, okay, these 2 different slopes, that means something to me. This amount of separation up here, maybe I care about that a lot, maybe I don't. I don't know. It depends on your study. But we can get a picture of how the outcome is predicted by the predictor for different levels of the moderator. That's what this picture is.
Actually, if you look at the graphs and the confidence intervals, you can tell where the area of significance starts for X around -1.
Yes. Yeah. So around here is where the top of the red 95% confidence interval crosses the line for the blue estimate, and so to the right of here, they are significantly different from each other.
Could that be useful for maybe doing experiments in the future?
What do you mean?
Like, say you wanna where their separation is,
Mhm.
and so now you gear your interventions towards those groups where you know that you can maximize differences.
Right. Especially when sometimes if you're really lucky, these lines don't really cross at all, and so that especially when the moderator is categorical and you have different groups having different regression slopes, you could say this intervention is very effective for this group and not effective for that group. It might not be worth applying your intervention to all people. Maybe it only works on one class of person. But so you have an intervention to increase, why not college navigation goal setting? People actually doing the stuff they're supposed to do to apply to college. But it only works on one particular group. It only works on hockey players. Just making something up, right? Well, if I want my hockey players to apply to college, I can use my intervention. If I want my math team people to apply to college, that intervention might not be useful. It was only useful for the hockey team. So yeah, you can, especially when the moderator is categorical, you can identify different groups on which it works and at different levels.
Can you go back a slide
Yeah. You meant 2 slides.
to the syntax? Are there questions on this slide?
M+ has a built-in command inside of model indirect called mod that is useful when you have moderated mediation, which we don't have here. When you just have moderation, this is how you do it. But if there's moderated mediation, it'll automate a lot of this for you. So if this was not a direct effect, but rather an indirect effect, if, way back in my original example, if the path between achievement and self-esteem was moderated, then it would automate a lot of this stuff for me with a command called mod. But yeah, this is what it looks at. This block down here produces the graphs. This block here produces the slopes of those graphs. And this block up at the top is just declaring what I mean by high SES and what I mean by low SES.
Could you remind us again the values that go in the statement line loop?
Okay, so let's talk about the plot line first. Plot y variables. So on the y-axis, it's going to have college navigation goal setting at low, medium, and high values of SES. So plot, these are your y variables, the things you're going to graph. Each one of these ends up being a line in your graph. Okay? And then in loop tells it how to do the x-axis. So loop, and then the name of my x variable, I can call it anything I want. I can call it Bob, and then I'll put Bob here. In our case, the x variable, what it really is college navigation self-efficacy, but I can't name it CNSE because that's already taken, so I called it x instead. And then the low and the high values, I went from -3 to 33, roughly -2 standard deviations to 1 standard deviation. And the -33, roughly -2 standard deviations below the mean, +33, roughly +2 standard deviations above the mean. And you'll kind of adapt those to capture your sample, right? You want to see everyone in your sample, or more or less everyone in your sample. If you make it too wide, then all your concentration is in the middle. -2 to +2 standard deviations seems to work pretty well. And the last number is a step size. So it doesn't actually create a continuous plot. It calculates the value at different points and connects the dots. And so this is how far away those points are. So what it does is it calculates this, CNGS low, at x equals -32, or -33, and then -32, and then -31, and then -30, and then -29, and so on and so forth, and connects the dots to create that graph. But I could make it more fine-grained. If I think that there's a really subtle effect that I want to catch, I'll make it more fine-grained. But this is just a step size. Set it to whatever makes sense. Make sure there's at least, say, 20 steps between the low and the high, and you should be fine. In the output, it'll give us an estimate for the coefficient of the college navigation self-efficacy times socioeconomic status variable, the path from that onto goal setting. And it's very small, and it's pretty much always going to be very small in your model results. And the reason for that is because of the variance involved. This variable, the variance of this variable is the product of the variance of college navigation self-efficacy and socioeconomic status. Its variance is gigantic. So of course it has a very small parameter associated with it. It has a standardized coefficient. If you were to request standardized, and I did, then down below here it'll say standardized model results, SCDYX standardization. And if you look there, the coefficient is 0.155. Regression coefficient of 0.155 isn't gigantic, but it's certainly a lot nicer looking than 0.009. So if you're doing this, don't see a small number there and say, oh, didn't work. The standardized coefficient is sort of more informative, but what's really important, to me at least, is this picture. Right? This picture I can see, look, it's actually different, and depending on my setting, it's different in a way that's meaningful to me, or maybe it's not, but I can look at the picture and I can tell. Also, in our model constraints, we specified simple effects at low, medium, and high values of SES, and it tells us that slope. So the slope of goal setting on using self-efficacy to predict goal setting, that slope at low SES is 0.212. That slope at high SES is 0.535. So is that a big difference to you? I don't know. I said it's over twice as big, so maybe that's really important. Again, the interpretation is very difficult, except in the particular context of your study. I don't want anyone to come away thinking a difference of 0.3 is always amazing. It's not. It depends. All right. So some advanced issues. If you're interested in multi-level mediation analysis, this is a good paper to start with. If you email me, I can suggest a few more. And the predictor, mediator, and outcome variables, they can occur at any level. You can have as many levels as your software will handle. If you have categorical variables, I mentioned that a lot of times moderation analysis uses categorical variables. We have different groups, and our treatment works differently for different groups. But there's a lot of different kinds of categorical variables, and they can be at any spot. They can be categorical predictors, categorical outcomes, and we're doing logistic stuff. They can be categorical mediators, and then we're doing logistic stuff on one end and continuous stuff on the other, and it gets all kinds of crazy. But Bucci, I don't know how you pronounce his name, and I apologize if he ever watches this, which is unlikely. It kind of spelled out in that paper how to handle all these cases. Binary versus multi-categorical versus continuous. You want to know about it, and it's there. Mediation and moderation can both be present, and these models can get bigger with lots more variables. But if you have mediation and moderation, that can happen in two different ways: moderated mediation and mediated moderation. Moderated mediation is talked about by Hayes in 2015. He talks about how to analyze it, how to see if it's there, what it means. If you find yourself adrift in a sea of mediation and you don't know what's going on, look for publications by Hayes. He writes as well or better than any other author in this area. And Mutin and Asparov, in their regression and moderation book that they published last year, all of these analyses, especially if you're using M+, how to do them, what they mean, why they're structured the way they are in this textbook, is very solid. And they have some very complicated models. So if you're interested in something, I'm sure you can find it in their book. And finally, sometimes in education, our models can get pretty complicated. And the more complicated your model is, the more maximum likelihood is to tell you to pack your bags and go home. So Bayesian analysis, Gibbs sampling, MHRM, those fun things, they actually outperform maximum likelihood in terms of estimating some of these parameters and standard errors and things like that. So if you have very complicated models, and this bootstrapping thing is going to take until the heat death of the universe, well, Bayesian estimation methods might work for you. So I've got a bunch of references here. Don't expect you to read the list, but it's there for you to go see when this is posted on the APS Lab website. That's my talk. Thank you for coming.